Welcome to this third part of the series of talks, videos, whatever you like, with my attempt to wrestle philosophy into something like a more modern shape, to make it more adaptable, to make it more adapted to the situation that we find ourselves in today. My effort in that has been to try to expose some of the problems with the way that philosophy has traditionally been spoken of. Its emphasis on monadic properties, on properties that are members of that apply to only one thing, which really has its beginnings in Plato, since Plato's forms apply to one thing, and it's only, as it were, by applying the same form applying to two things that you get any kind of relations going within that structure of forms. Forms, I think, are a very crude way of understanding things because they leave out relations pretty much entirely when the relations are of a more complex sort. And then in the next video, I moved on to talking about things which don't really have a sensorial basis. For example, mass, velocity. Mass doesn't really have a kind of sense that you can grasp onto, and you will almost certainly be aware that then it's equivalent to energy. Well, what is that energy? That's a good question too. If mass isn't really something which you can have a sensorial observation of, you can't have a sensorial observation of energy either. But these things exist, and yet our philosophy doesn't properly accommodate them. And what I've been trying to do is to sort of see if that's a remediable situation, that we can somehow move philosophy away from its traditional core, which it sort of got into, I guess, in the 18th, 19th centuries, and then it sort of was preserved, one could say almost preserved in aspic from that point on, and it hasn't done it any favors to be encapsulated in this way. So the question to continue on from what I was saying last time, the question can be asked, well, if a velocity in Galilean relativity, velocity is something which is relative to a frame, a Galilean frame, and you can choose a frame, then what is velocity a property of? Can one even speak that way? Let's go back to the car analogy, which is very familiar to everyone. You're driving along, well, there are two obvious reference frames. First of all, before you get in the car, your reference frame is, well, you're not moving at the moment, you're just standing there. So you're still, okay, that's fine. You feel nothing of that stillness. It doesn't have a feeling attached to it, which is any different to the feeling which is attached to going along at a steady speed in a straight line at 20 miles an hour, or 60 miles an hour, or 80 miles an hour, or 200 miles an hour, or if you were in a spaceship, 1,000 miles an hour. So there isn't a sensorial basis to that. But the more fundamental question is, what is a velocity? Can we think of it as a property that a thing has? Remember, in the sort of traditional way of thinking about these things, which comes really from Aristotle and Plato, we only have two things which we can assign things to. They're either properties, attributes, or they're individuals. What is a velocity? We got logic in the form that we've got it because philosophers wanted to update and make more versatile the whole legacy of Aristotle's logic, the Aristotelian syllogistic. That was thought to be something which needed to be fixed because there was a very strong view in the beginning of the 20th century that Aristotle's logic was something that was just irremediably broken. It could not do very much, and what it did do, it did not do particularly well. So there was a need to come up with something that would replace it, and that was done. That was quantificational logic. We had already in the Middle Ages a pretty well worked out propositional logic, which was then further, in a sense, fixed by Wittgenstein in the Tractatus and by Emil Post to give it decision procedures, which are truth tables, etc. So we have a tradition of logic which somehow, which carried on, which replaced the Aristotelian logic of before. You can find plenty of articles online from very good logicians saying how bad Aristotle's logic was. But Aristotle's logic is really a sort of logic which is based on the idea of forms. It's based on the idea that things have monadic properties. There aren't really relations in Aristotle's logic at all. So what Plato invented, Aristotle carries over into his logic. And quantificational logic does sort of fix that problem, because in quantificational logic you have relations which you can quantify over, even if those relations aren't fleshed out, if they don't have much of a clear say in what's going on, if they're not labeled clearly, we can still talk about them, and that's a big step forward. The metaphysics didn't quite take the same step forward. But okay, let's leave that for a minute. What is a velocity? It's a vector quantity of what? Now I say that the only good answer to that question would be it's a property of not a thing. It's not a property of you in your car, because you in your car would have contradictory properties. Be in two different frames at the same moment. You can be at rest in your car driving along at 60 miles per hour, and yet with respect to a frame of reference that's situated on the sun, you're going at a vast speed because the Earth is spinning and the Earth is also rotating around the sun. So if the sun is at rest, you take that as your reference frame, you are going at a very great speed indeed with reference to that. But that's a contradiction. How could you have, if it's a property, how could one thing have contradictory properties? How could you be going at 20 miles per hour, but also in a different frame, 60 miles an hour, or 2,000 miles per hour, all simultaneously with different frames? So what we have to say, I think, is something like, we have to distinguish between, if we're not going to get involved in contradictions in logic, then we have to say, well, there are frames of reference, and it's only within those frames of reference that something is attributed, has a property attributed to it in that frame. And that makes some sense, although I think the idea of a property attributed to it is probably a misnomer. We really have a predicate attached to it, to something. We don't have a property really at all. We have just something like a predicate which is defined within reference frames. I'm not sure that we have a good, clear way of saying that within logic. But let's come back to that point at the end. Okay, that's really where I want to. First of all, I want to clear up something, because it runs in the back of everything, and everyone who talks about relativity is really a little bit misled and led astray on this matter. Particularly, I think, people who talk about relativity of truth, because I think they're grasping onto this in a way which is illegitimate. Let me just start off by saying that it was Einstein who really branded his theory a relativity theory. In that he was contributing to a view that was very well established within mathematics, that had been established for the past, I think probably by that point, maybe 30, 40 years. And in that, what you're doing is you are looking at a group which acts on some kind of space. The things which that group will leave in place is called an invariant. And the things which the group changes as the group actions change from one moment to another would be called something which is relative elements. So you have invariant elements and relative elements. Invariant theory was one of the most hard-working and developed and strenuously developed areas in mathematics at the end of the 19th century. Now, when Einstein came along and talked about relativity theory, he was really referring to the velocities that are relative, but that had already been the case in some ways in Galilean relativity. But he was also talking about the relativity of time, how your temporal intervals will depend upon your velocity, and also things like length contraction. It's called the Lorentz-Fitzgerald contraction of an object as it's going, it has its speed, as it has its velocity. And those two things, the temporal durations and the Lorentz contractions, in some ways tied to one another and play off against one another as in relativity theory that is developed by Einstein to go beyond Galilean relativity. That is the way in which it goes beyond. But there are other things which are not relative, and this is really an important point. There are things which are not relative at all in Einstein's relativity theory, and the obvious one is the speed of light. The speed of light is a constant in Einsteinian relativity theory. Now, when Minkowski came along a couple of years later and after Einstein had published the paper, what he did was emphasize the invariance in the relativity theory, the invariance being the speed of light. Now, that defines cones in the space. They're called light cones, and they're the cones along which light travels. And those cones are invariant under the relevant group. The relevant group in this case being the Lorentz group. So Minkowski wanted to emphasize the invariance. As a mathematician, that was what he wanted to link into the whole tradition of finding invariance for groups. The light cones are invariants for the Lorentz group. And in some ways you could say, well, it's the invariants that really define the group. They are the important things. And what's relative, well, it's important. What's relative may be important to us, and it may get the theory more of more attention from the ordinary public, because if they're told, well, the length of something is dependent upon the speed in which the object is going relative to light. If they're told that, then it sort of galvanizes the public. Oh, things are relative. Things are relative, more relative than we could ever have thought they were before. Though most people, of course, didn't have any understanding of Galilean relativity. In fact, the whole idea of Galilean relativity, it has to be said, only became talked about in probably the 1960s, maybe the 1950s, long after the development of Minkowski relativity, or the Minkowski-Einstein theory of relativity. People would latch on to this idea of, well, things are relative in relativity theory. And Minkowski wanted to push against that. He wanted to insist, no, relativity theory is really a branch of invariant theory, where the invariants are invariants with respect to the Lorentz group. And that's the important thing. It's not the things which are relative, which define the theory. It's the things which are invariant. And the light cone is the invariant structure of relativity theory. When people took Einstein's theory and sort of took in the idea of relativity theory, they sort of ran with it in a way which made no mathematical sense. They tried to say that, well, truth is relative. Truth is relative to what? How does that make any sense at all? I'd suggest that it doesn't, and that's why philosophers tend to dismiss this idea and not talk about it. Why it gets talked about by people who are not philosophers, mostly people in other arts areas, like, say, for example, English or history or something. People who don't really understand philosophy at all have grasped onto this idea, oh, there's a relativity of truth. In some ways, Minkowski was right to push back against Einstein on this matter. And by the way, I should say, Minkowski was Einstein's teacher. He had been his teacher a couple of years earlier. Minkowski was right to push back against Einstein on this matter because it was almost as though he could foresee that this was going to be misleading, that this was going to lead to people thinking that, oh, everything's relative, but a common expression these days. Everything's relative, therefore, whatever. That idea was sort of, something that Minkowski tried to head off by taking it back to the mathematical context and saying, no, the theory is really defined by its invariants, and invariants have a long tradition in mathematics, and we can talk about those and understand them, and we can get more of an idea of the development of the theory and the foundations of the theory if we do. And that's how he came up with Minkowski's spacetime. It's basically a theory of what are the invariants of Einstein's relativity theory. Relativity theory is just something opposed to invariant theory, or a sort of a cockeyed way of putting invariant theory. But it's not entirely a cogent idea. If people want to speak about relative truth, well, ask yourself, all right, what are the invariants in that? And most people never answer that question. They're never asked that question, ever. Relativity theory only makes sense in invariant theory. Things are relative versus those things that the group leaves invariant. That says something about relativity theory and velocities in Minkowski's spacetime, or in relativity theory, if we wish, Einstein's relativity theory. Then the velocities are relative to frames. Now they're relative to Lorentz frames. So we have Lorentz frames, which are frames in which the Lorentz group moves between, and the things that are relative will change from one frame to another under the action of the Lorentz group. That's what relativity really says. I talked about the problem of reconciling this with quantum mechanics last time as well. I pointed out that there is a relationship between position, which strictly position doesn't exist in relativity theory. It's, again, something that's relative. You have to really sort of extend yourself into what's called the Poincaré group rather than the Lorentz group, which makes that more clear, but that's doable, and people do it in physics every day. As I said last time, there's a sort of pairing up of position and velocity. Momentum is mass times velocity. Mass is a constant, usually, or you can make it something which is relative as well. And early on that was done. You have these ideas of mass and velocity, or mass and momentum, and those things are paired up. And this introduces a new element. They are said to be non-commutative in their action. A times B equals B times A, because multiplication of ordinary numbers is commutative. That's what the word commutative here means. A times B equals B times A. It's commutative. Addition is also commutative. A plus B equals B plus A. It's commutative. But in quantum mechanics, the operators which we are dealing with of position and momentum, or position and velocity, if you want to strip mass out of it, these operators, which are usually in physics represented as by matrices, are non-commutative. And that was the big discovery by Heisenberg in 1925, 100 years ago, pretty much to this day, very close anyway, you know, June, July, middle of the year. He was staying on an island, Helgoland, which I think is the name of it. I think this was also the title of a Massive Attack album. I don't know whether it was because of Heisenberg, because I'm not sure that Helgoland is really famous for anything else. But anyway, it was where Heisenberg was staying when he came up with this idea that the mathematics of quantum mechanics involved non-commutative multiplication, and it did so because these were matrices that were being multiplied together. And if you did matrices in school, and I hope that at least some of you did, then you'll remember that A times B is not equal to B times A. If you have matrices that are of the same shape, you can turn them around so that you can do A times B, and you can also do B times A. But you don't get the same answer. A times B with a matrice is different from B times A. And that's what Heisenberg attached himself to. He didn't know much maths. This was a wild guess, and he thought of it in the middle of the night. And then, having thought of it, having realized it, he went down and he stood on the cliffs of Helgoland and just watched the sun rise, knowing that this was an important thing to have discovered. He was so right. So right. That was 100 years ago. 100 years ago, this idea of non-commutative multiplication, where the things you're multiplying are matrices, first hit in the idea of explaining quantum mechanical entities. And it has been with us ever since. I don't remember when I was in school, we did do matrices, and we did do the fact that they were non-commutative. I don't remember ever being told that this was one of the great discoveries of the 20th century and that it made quantum mechanics possible. Don't think there was any mention of that at all. I hope that's changed now. I hope that it has. I'm sure it has, really. Anyway, that was the big discovery, this non-commutativity. Now, but then you have a strange relation between these two, what look like reference frames, because you've got one frame in which you've got things having a place, position, particles having a position, and on the other you've got things having a momentum, mass times velocity. And those two are non-commutative, the operations are non-commutative, and you can't find out, because of that, you can't find out the position and the momentum simultaneously. You can do one followed by the other, or this one followed by this one, but you can't do them simultaneously, so you can't find out the mass, sorry, I keep saying mass, you can't find out the position and the momentum at the same time. So you've got this a very strange relation between these two things, position and momentum, position and velocity. That's the beginning of quantum mechanics, but now we get these strange relations between these things. I've said that certain things are invariant in relativity theory, and the light cone is one. So the speed of light is an invariant. There are other things which are invariant too. There are things called, I'm not going to try to explain this in this video, but there are things called spinors, I should say. I should emphasize it, spinors. Spinors are also, thanks to Dirac in 1928, are also invariants under the Lorentz group. That was one of the most powerful and astonishing discoveries in this electrifying 10 years of discovery. From 1925 to 1935, it was like 1 week after another things were being discovered. It was an astonishing time. it happened so fast that it was very hard to keep track of who was discovering these things and what contribution they were making. Everyone was contributing to this vast explosion of understanding, and the explosion was very, very quick. By 1928, 3 years after 1925, there was a vast explosion in the whole idea of how groups behaved in this way in quantum mechanics, and also an explosion in the understanding of new things which were discovered, things called spin and spinors. And those things, it was discovered by Dirac, are Lorentz invariant. They don't change when you change the Lorentzian frame. That was astonishing. 3 years after the subject was invented, almost. That 1925 was almost the moment of invention. And 3 years later, we had this enormous discovery, a quantity that no one had any idea of really before Dirac. There were mathematicians who had sort of dabbled in this and who did say things about this, but to the physicist, the idea that this was a physical idea, that was entirely new. That was new ground. But that's what Dirac did. Dirac is not named in the same way that we name Heisenberg. He doesn't have something very memorable named after him as Heisenberg does, the Heisenberg uncertainty principle. But Dirac was probably more powerfully involved in the formulation of quantum mechanics than anyone else at that time, including Heisenberg. Because Dirac did have the maths. He was a mathematical genius. And he had that maths beyond almost anyone else. And when he came up with this idea of four-dimensional or four-component spinners, that shocked everyone. Everyone was astounded by this discovery. That was a more powerful discovery than anything that had come before, because it showed that there were quantities that went quite beyond the quantities that were being used traditionally, vectors and operators and etc., tensors. These were new things, and it ushered in this idea that there was a new quantity of matter, a new attribute of matter, which had been discovered at that point. And it also ushered in simultaneously the whole idea of antiparticles. It was true that Dirac invented it all in one paper. That was the most amazing thing. And for that, Dirac, along with Heisenberg and Schrödinger, won the Nobel Prize in I think it was the early 30s. He should have gotten it, probably by himself, but he shared it with Heisenberg and Schrödinger. That was astonishing work, groundbreaking work, and it changed everything from that moment on. There's probably no greater discovery in the beginnings of quantum mechanics than that. And everything then, the mathematicians really then set to work on trying to understand what on earth these new quantities, these spinors, actually were. And that work continued on through the 20th century. The best place to find this is, by the way, the book, which I heartily recommend, the book by Penrose called The Road to Reality. That book contains excellent, not too difficult, expositions on this matter and also the Minkowski matter. All of this is covered in The Road to Reality. So if you want a single book that goes with what I'm saying in terms of the physics, that's it. Now, going along with all of this, there is a reformulation of the idea of space and space-time. Even in Galilean relativity, you can reformulate Euclidean space to incorporate Galilean relativity. It gives you what was called much later the idea of a fiber bundle, which gives you the idea of fibering the space to sort of as a way of getting time-like lines associated with space-like planes. that choosing the fibration, choosing which fiber you're in, is a way of choosing the frame of reference. Now, in Galilean relativity, there was no finite velocity to light. So if we want to say, if you want to understand the relationship between Galilean relativity and Minkowski-Einstein relativity, then it goes like this. We've got these cones. These cones in relativity, Einstein relativity theory, Minkowski relativity theory. If we unfold them so that the speed of light goes to infinity, then those cones lay flat as a plane. And so does the past light cone. It flattens out into a plane. That gives you these planes into which you are fibering the space in Galilean relativity theory. Once you take those flat, the two, the forward and the backward flat planes, and you form them back into a cone, then that's how you get Minkowski spacetime. It's as simple as that. You take these flat planes and you fold them up into something which gives you a finite speed of light. So you get these as separating off the regions which you have experience of. You have experience of the light cones. You have experience of what is within the light cones. What is outside the light cones, you have no experience of whatsoever. If you think, well, I want to understand what space is like, the space around me, there's no point attributing any of that to the space-like regions that are outside the light cone. Because if you think you have experience of space, sure, you don't have experience of space-like regions at all, so they can't be the same at all. That's a mistake that many people make, and it misleads completely on this topic. But just drill it in. You don't have any experience of the space-like regions in Minkowski spacetime because nothing travels faster than the speed of light. If nothing travels faster than the speed of light, then those regions are lost to you. They cannot serve as any basis for your evidence. Okay. So we have these notions of space which come from relativity theories. Galilean relativity theory has a Galilean space-time. It's not very well known, but it exists. There is a different space-time, Minkowski space-time, which goes with the Einstein relativity theory. Now the question is, how do we understand these new spaces, these spaces that are not Euclidean? How are we to understand them? Well, that has really been one of the great sagas of the 20th century, trying to get a better understanding of what the space-time is that we exist in. It changed again when general relativity came out and these spaces turned out to have curvature. Now, these spaces, these geometries, have algebras attached to them. There is an algebra attached to Minkowski spacetime. If you take just a simple two-dimensional flat version of Minkowski spacetime, which you neglect two of the spatial dimensions and just have a two-dimensional space, a plane, which has light cones, quotes on it, you get a structure of, in maths, called split complex numbers, or they're also called double numbers. They're also called, and this is probably the best name for them, hypercomplex numbers. These entities give you an algebra of the space. These algebraic objects make sense in a wider algebraic context called Clifford algebra. Now, in a past, I can't remember which one it was, but in a past video, I sang the praises of Clifford because Clifford came out with probably one of the best epistemological pieces of advice that had been given in the 19th century, which was you shouldn't believe anything for which you don't have sufficient evidence. That idea was somewhat new in this context, but it was made famous by William Clifford in a paper called The Ethics of Belief. That's not what Clifford is by and large known for. He's not known for that contribution. He's known for something else, something called Clifford algebras. And Clifford algebras enfold, they contain these split complex numbers. They contain the four-dimensional versions of split complex numbers in which you have 3 dimensions of space and 1 dimension of time, and you then have different variables that attach to those things in which you can manipulate. The main thing about these split complex numbers, I'll just describe them to you if you know already what a complex number is. If you know what a complex number is, it's a plus b, where a and b are real numbers, a plus b multiplied by the square root of -1. One of these split complex numbers, or double numbers, what these things are is simply a plus b, where a and b are real numbers, a plus b, where b is multiplied by I, capital I, and I, capital I, is the square root of 1, where the square root, we are not considering 1 or -1 as the square root of that I. It's a new square root of 1. This idea makes sense of Minkowski spacetime in algebraic terms. All that said, let me come back to the question that I started with. How does logic deal with any of this? Space, time, algebras? How does it deal with the idea of relative predicates or relative quantities, relative magnitudes? You get a contradiction if you try to insert them straightforwardly. So something has to be changed. What? I don't think there's has been any attempt to reformulate logic so that it makes sense of these objects, these things that are relative. Relative times, relative lengths, relative velocities. How do you do that? You have to introduce something else. Something like the logic within a frame where you relativize the quantificational aspects to a frame. I think that's the only way I can see of doing it. None of this really has much of effect on propositional logic, but it does have a real effect on quantificational logic, which is why I said last time that what quantificational logic seems to do is enshrine the idea of properties, predicates, and individuals in a way which is injurious to us. And I think that that's not a good thing. We need to have a more flexible logic so that we can deal with these things. And the same is true in quantum mechanics. Quantum mechanics does not give rise to, or is even properly expressed in, a quantificational logic. And when a very famous and important mathematician, John von Neumann, when he made the attempt to to put forward a quantificational quantum logic, he pretty much had a nervous breakdown over it. He tried for several years and he couldn't do it. And he was one of the brightest of the bright. He was a genius. So we have a violent need for reform here. We have 2 very big provocations requiring reform: relativity theory and quantum mechanics. And we need to reform logic to make some sense of these things. It's no good us teaching these things to students when they are ill-adapted to the 20th century world, and they are. Once had a colleague, I think he was one of the brightest philosophers I've known. He was, I think, a great philosopher. His name was Georgi Marcus, but we always called him George Marcus. George Marcus was a continental philosopher of the sort of the very educated Hungarian school. And he used to say, why do we need to teach students logic at all? And I thought that was wrong. I thought we did need to teach students logic. I mean, I would have stuck with that. Students need to know logic. But if his point was somewhat different, if he'd made the point by saying, why do they only need to teach logic, then I would have been inclined to agree with him. I was struck from the very beginning of philosophy with this, that it was a strange idea. Why was logic, why was one branch of mathematics, one area of mathematics, treated as though it's the only thing that philosophers need to know? I could understand this a little bit in the case of propositional logic because it's more flexible. But in quantificational logic, why? Why be restricted in this way? How are you even going to deal with, how are you going to express vector quantities in that system? How do you express operators? How do you express the relationship between operators and vectors? How do you do any of that? How do you express all of the rich structure of 20th century mathematics in that framework? I don't see it. I don't see that you can do it. And if you can't do it, maybe that's one of the reasons why metaphysics hasn't moved on, how it hasn't embraced the 20th century. One of the things that I would like to see discussed at length in metaphysics in the 20th century now, 21st century now, what I would like to see expressed is relativity. What is it? How do we understand it? What is the logic of that? And going on from that, how do we adapt to quantum mechanics? I think that's all, valid questions. And if George Marcus, he was, by the way, a lovely fellow, he was, very nice, and one didn't like disagreeing with him on anything. But, if one was going to disagree with him, what I would disagree with is, well, why is this the only thing that we teach students? Why is this somehow the only thing they need to know as a requirement for philosophy? And I don't see it. I don't see that it should be. But, philosophers tend to disagree about this, and, we tend to stick to our guns. I'm with them. I think we should teach logic. I just don't think we should only teach logic. But, and maybe that's what his point was. Why is this the sole thing which is sort of taken to be the heart and soul of the philosophical education? And, on that I would agree with him. So that's my point in this part of the series, that what we have here in these various things that I've been discussing are multiple strands which don't seem to fit in with logic, that suggest that we need to reform these things in order to take account of them. I don't think we've made any effort to stretch logic to accommodate these things, and yet we're 100 years, almost to the day, 100 years into quantum mechanics, and we're certainly more than 100 years into relativity theory. And yet we haven't moved. And that's where I leave you for today. Please watch the previous videos for this series as well, the first and second. This is the third. Hopefully there will be a fourth.